Let's now consider our fourth example, and that is a parallel plate capacitor where we have two different dielectrics in a series. So we have epsilon 1 and epsilon 2 here. And we want to calculate the capacitance for this system. Again, as by convention, I would call the top conductor to be conductor 1 and this to be conductor 2. I would release charge Q on the top and charge minus Q on the bottom. Now the first question which again comes is Q uniformly distributed? In this case, previously with parallel dielectrics, we had seen that the charge would not remain uniform. Now the question here is, would the charge remain uniform? Any point I go on the surface, I have the same dielectric below. Whatever are the polarized charges here, they would remain the same, and thus the charge on the surface should be uniform. Again, I'm neglecting the fringe effects. Under the approximation, A is much greater than the separation between the plates. Charge should be uniform. And thus I get a charge density Q by A. The next step I have to do is calculate electric fields, and I have two different dielectrics, so I need to calculate the electric field in the dielectric here, and then I need to calculate the electric field in the second dielectric. And again, we can just use our Gauss law to calculate the electric field over here. We make a Gaussian surface like that. And nothing has really changed from our example 2. The electric field we will get here would be rho by epsilon 1. Now, there are polarized charges in the two dielectrics, but the new version of Gauss law we are dealing with only has free charges. That's all that matters in the new version of Gauss law. So where are the free charges present? The free charges are only present on the conductor. That's all that matters. So to calculate the electric field at the bottom, I can still make a Gaussian surface, cut this through epsilon 1. Doesn't really matter because there is no free charge enclosed in that region all the way to epsilon 2. And if I do that, free charge is only present here. The electric field I would get, let's call this E2, that would simply be rho by epsilon 2. So we have electric field E1 in dielectric 1 as rho by epsilon 1, and electric field E2 in dielectric 2, rho 2 by epsilon 2. Now we have to calculate the potential difference, which is going from conductor 2 to conductor 1. So we have to choose a path. So let's say I choose a path on that red line. When I walk from here to here, electric field is constant. So the potential difference on that part would simply be rho by epsilon 2 d2. And when I walk from here to here, electric field within that region is constant 2. And I'm walking a distance d1. So there it would be rho by epsilon 1, the electric field in that region, which is a constant, the total length I travel in that region, which is d1. And we can substitute the values of rho, so we would get q by a epsilon 2 d2 plus q by a epsilon 1 d1. That becomes 2 to 1, potential difference between 2 to 1. Now we can calculate C. Let me just change this form a little bit. I'm going to write this as A epsilon 2 by D2 plus Q A epsilon 1 by D1. So if I calculate, we have seen delta V across our conductors is Q by A epsilon 1 D1 plus Q by A epsilon 2 D2. So if we now want to calculate our capacitance, that would be Q by delta V 2 to 1. And substituting those terms, we would get 1 by 1 A epsilon 1 D1 plus 1 by A epsilon 2 D2. Let's rewrite it as 1 by C. We would get this as A epsilon 1 D1 plus 1 by A epsilon 2 D2. However, this is the capacitance of the first dielectric, and that is the capacitance of the second dielectric. So what do we see? That when we have two dielectrics in series, we create a capacitance C1 and a capacitance C2, epsilon 1 and epsilon 2, where C1 is epsilon 1 A1 by D1, C2 is epsilon 2 A2 by D2. When we have these two in series, we create an equivalent capacitance which behaves like that of parallel resistors. The inverse of the capacitances add up to give the inverse equivalent values. Again, you will see this in ECE 140 also, when you analyze capacitors in series and parallel. But we have to be careful. We have to be a little bit careful in understanding what we are doing. In first year books and many online terms you see, many online forums you see, you would have problems which would be conductor, and just to make your life difficult, there would be three dielectrics placed. So you have epsilon 1, arbitrarily given names, epsilon 3. And the solution in these forums is you have a capacitance C1, a capacitance C2, a capacitance C3. So the equivalent capacitance would be something like this. There is a big conceptual problem here. This is a very rough approximation. It would work well if these all the terms are very large, but mainly as EC engineers, you are not going to be working with that large sizes. It's a problem which is given just for the sake of making a problem. But you end up creating a big conceptual difficulty here. Let me tell you what that is. What you have is three dielectrics which you have two seem to be in series, one in parallel. Let's say this was epsilon 1, epsilon 2, epsilon 3. We would have an electric field, let's call it E1. There would be electric field E2 and an electric field E3. E1 has to be equal to E2, at least according to these calculations, because they are tangential. If I just go at this boundary, you have E1 and E2. They are tangential there. So E1 has to be equal to E2. But E1 has to be also equal to E3. Right here. They're tangential to each other too. They have to be equal. However, E2 is normal to E3. Right at that boundary. And what did we learn? We learned epsilon 2 E2 should be equal to epsilon 3 E3 because there is no free charge here. The normal boundary condition is that E2 cannot be equal to E3. These cannot be equal. There is a discontinuity in the normal electric fields. There is the tangential electric field is equal across the boundary, but the normal electric fields are different across the boundary. If there is no charge, at least if there is no charge present on the boundary, there's no way they can be equal. These three cannot be true at the same time. What is going to happen in a structure? What is going to happen in a structure like this is that there is going to be a very, very strong fringe field right at that junction of the dielectrics. So it said there was one dielectric here, there was another dielectric in this region, and a third dielectric here. We are going to create a lot of induced charges at that point, and if you look at the fields, there is going to be strong fringe fields or fringe-like fields which are going to be created at that point. Yes, far away from that fringe fields, things may start to behave. So if your dimensions are large enough that you again neglect these fringe fields, Then you can approximate it as a capacitance C1 in parallel to C2 and C3. If you neglect those fringe fields, that's why I have been always emphasizing right from the beginning of the course, it is very important for us to understand what we are doing. Because once we understand it, then we can make the approximations. We can see whether our approximations are correct or not. We should not just go blindly if you have a structure like that. And you see structures like that when you do MEMS kind of devices, micro electromechanical systems. You do see some structures which would be created like that. And if you start blindly applying parallel and series components there, you may get wrong results. So understand what we are doing. If we understand what we are doing, then we can decide whether those approximations are correct or not. Just don't blindly do things. All right. That was example 4 with dielectrics in series.